Welcome to The Explainer. Today we're going to break down how to build a scientific theory. And forget what you might be imagining. Dusty labs, complex equations. Instead, I want you to think of yourself as an architect. But you're not designing buildings, you're designing powerful ideas that help us make sense of the world.
Okay, to get us warmed up, let's start with a quick quiz. Take a look at these 5 statements. You've probably heard some of these before, right? What do you think they all have in common?
Yeah, if you had a feeling that something about them was just a little off, you nailed it. Every single one is a really common misconception about what science is and how the whole process of discovery actually works. So, let's fix that. In this explainer, we are going to walk through the actual blueprint for building a really solid theory. We'll start from that first little sketch of an idea and take it all the way to the ultimate test, causality. All right, first things first. Before we can start drawing up plans, we've got to be on the same page. In everyday conversation, we might say, I have a theory, when we really mean, I have a hunch. But in science, it's a whole different ballgame. So what exactly is a scientific theory? Well, it's definitely not just a hunch. It's a model. The best way to think about it is like a map. A map isn't the actual city, right? It's a simplified version that leaves out a ton of details so you can see what you need to see to get from point A to point B. A good theory does the exact same thing for the world. It simplifies things so we can understand the why behind what we observe.
But of course, not all theories are created equal. You can't just throw one together. A really strong theory has to have solid foundations. So let's look at the 4 essential features that separate a truly groundbreaking idea from, well, a house of cards.
So every good theory needs these 4 pillars. It has to make sense on its own, it has to actually explain something important, and it should be as simple as it can be. But I want to draw your attention to that 3rd pillar, falsifiability. This, right here, is kind of the secret sauce of all scientific thinking.
Now, this might seem a little backwards at first, but a statement like, the sun revolves around the Earth, is a perfectly scientific statement. Why? Not because it's true, we know it isn't, but because it's testable. We can go out, make observations, and prove it wrong. See, the whole point of science isn't about getting right, it's about making claims that could be proven wrong. The invisible, undetectable dragon? You can never prove it's not there, so that's not science. Okay, so with that in mind, where do we even begin? How do you actually start drawing the plans for your own theory? Well, it almost always starts with something really simple, just noticing something interesting, a puzzle or a pattern out in the world. The best starting point is to look for variation. Find something that changes from place to place or over time, and just ask, why? Why is it like this here, but like that over there? That question, that's the spark. That's the raw material for a fantastic theory. Take a look at this chart. It's showing military spending as a slice of the economic pie for a few countries. The variation just jumps right out at you. And that immediately sparks a question, doesn't it? What causes one nation to spend a ton on its military while another spends very little? And boom, just like that, you have the seed of a theory. Now, once you have that question, you can basically take one of 2 paths. You can go the inductive route, that's kind of bottom up, where you start with specific observations and build up to a general idea. Or you can go deductive, top down, where you start with a big general principle and use it to make a specific prediction that you can then test. And most new theories follow one of these 3 strategies. You can either try to explain a totally new phenomenon, you can find a new cause for something we already know about, or, and this is a really cool one, you can find some other factor that changes a relationship we thought we already understood. Okay, so our blueprint is starting to come together. But a drawing is one thing. How do we know if the building will actually stand up? Well, we have to stress test it. And that means we need to translate our big, broad theory into something concrete and testable. We need a hypothesis.
A hypothesis is where the rubber meets the road. It's the direct, testable prediction that comes straight from your theory. It makes a clear claim about the relationship you expect to see between your cause, the independent variable, and your effect, the dependent variable.
And hey, if you ever want to write a fantastic hypothesis, this template is your best friend. Seriously, it forces you to be super precise about who you're comparing, what the cause is, and exactly what effect you expect to find. And look what happens when we use it. We get these crystal clear, totally testable statements. We're directly linking a concept like political party or government type to a specific, measurable outcome.
These aren't just wild guesses anymore. They are precise predictions ready to be put to the test.
Which brings us to our final and maybe the most important step in the entire process, the quest for causality. This is like the final inspection on our building. We have to be absolutely sure that what we're seeing is a real relationship and not just some random coincidence.
We've all heard this a million times, but it is the golden rule of all science. Correlation does not equal causation. You know the classic example, right? Ice cream sales go up at the same time drownings go up. But does eating ice cream make you drown? Of course not. There's a hidden factor, hot weather, that's causing both things to happen. We always have to hunt for that hidden factor.
To really claim you've found a cause, you have to clear 3 big hurdles. First, the cause has to happen before the effect. Makes sense. Second, the two things have to actually vary together. And third, this is the big one, non-spuriousness. You have to do the hard work of proving there isn't some other hidden variable pulling the strings. And that last hurdle, non-spuriousness, that's what separates the good theories from the great ones. It takes a ton of critical thinking to make absolutely sure that the relationship you're seeing is the real deal, and not just some illusion created by something you haven't thought of yet. So here's the bottom line. Building a theory isn't some vague academic thing. It's a powerful step-by-step process. The theory is your blueprint. The hypothesis is the stress test. And a true causal explanation, well, that's the finished, solid structure that helps us truly understand our world.
And that leaves us with one final thought. Now that you've got the blueprint, look around you, at work, in the news, in your own life. What's a puzzle you've always wondered about? What's out there just waiting for its architect?